Today we will see how timer 0 is used of PIC16F877A. For timer 0, these are the features you can read out. Then the timer 0 is associated with the following three registers: timer 0, INT-con, and option underscore reg register. So how these registers are used, that we will see in the next slide. So the timer 0 module will increment with every instruction cycle. The instruction cycle is not equal to the oscillator cycle. Okay, so the oscillator cycle is different and the instruction cycle is different. 4 oscillator cycles are taken for getting one instruction cycle. Okay, so the timer 0 increments with every instruction cycle, not with the oscillator clock cycle. The prescaler module is shared with the watchdog timer. There is a prescaler module for the timer 0 and this prescaler module is shared with watchdog timer. In this case, PSA, PS2, PS1 and PS0, these are representing the prescaler. Okay. Now, if PSA is equals to 1, okay, then this prescaler belongs to watchdog timer. Okay. This prescaler belongs to watchdog timer, and you can see by default the option underscore reg register has value of all 1. So that means PSA is equals to 1. So this will belong to watchdog timer. So in this particular configuration, the prescaler will have no effect on timer 0. Now this timer 0 counts up, and from 00 hex it goes to 255, that is FFX, and from FFX when it again goes to 00 hex, then this particular flag, this particular TMR0 IF bit gets set. Okay, so through that we can understand that the overflow has happened. Okay, so if TMR0 IF overflow interrupt flag bit if is equal to 1, that means overflow has happened, and if it is equal to 0, that means overflow has not happened. Now this TMR0 IF is part of INT-con register. Okay, the INT-con register is the main interrupt config register. Here you can find GIE. GIE is a global interrupt enable bit. Okay, now if it is equals to 0, then it disables all the interrupt. Okay, and by default you can see this is all zeros. So that means GIE is equals to 0. So that means none of the interrupt can work. But this TMR0 IF, the TMR0 IF is not the interrupt. The TMR0 IF is the flag. So this will be generated irrespective of GIE. Whenever timer 0 or TMR0 overflows, the TMR0 IF will be set. It does not depend on the GIE. If it is 1 or if it is 0, that does not depend on that. Now there is another one, T0CS. The T0CS actually starts the timer. Okay, whenever you clear the T0CS bit, then it will start the timer. Now you know the timer increments with every instruction cycle. So that's why you can configure that on which edge, rising edge or trailing edge, you would like to increment the timer. So for that T0 AC is there. If you clear T0 AC, if you clear this T0 AC, if you clear this T0 AC, then it will consider as the rising edge to increment. So this is the schematic. You can see port B0 will be toggled for each and every overflow, and this is attached to a oscilloscope. So this is the code for that. First we are defining the crystal frequency. Here we are defining our crystal frequency as 4 MHz. We are including the header file hec.h. We are starting the main file void main. We are making the port B pin number 0 as the output. So TB0 is equal to 0. Then we are setting initially port B0 as a 0. So RB0 is equal to 0. Then we are choosing the rising edge. So T0 AC is equal to 0. Then we are starting the timer by making T0 CS equals to 0. Then inside the while true loop, we are checking while timer 0 interrupt flag is not equal to 1. So if the timer 0 flag is not equal to 1, then it will do nothing. But whenever timer 0 flag will become 1, that means whenever the overflow happens, it will toggle the RB0. Okay. And also we have to clear the timer 0 interrupt flag. Timer 0 IF flag is equals to 0. Now we have to calculate the delay, how much delay it is getting generated. So here we are using clock frequency is equals to 4 megahertz. So 4 into 10 to the power 6 clocks come in 1 second. Therefore, one clock will take 1 by 4 microsecond time. This is clear. Now, one instruction takes 4 clocks. One instruction takes 4 clocks, so that one instruction cycle will take 1 by 4 into 4, that is 1 microsecond time. Okay. And the timer increments with instruction cycle. So, the timer value will be incremented by 1 in 1 microsecond. So how many values or how many counts are required to overflow? 256 counts are required to overflow. So that means 256 microsecond delay will be generated by this particular code. Now, if we go to this code in MPLAB IDE, so you can see the code here. I'll show you the code. So this is the same code that we have written in the PowerPoint, and you can go here project and rebuild this code. It will generate the hex file. Then you go to Proteus and double click the microcontroller, select the folder and the hex file, select the 4 megahertz oscillator frequency, click on OK, and just run this. So you can see the one clock frequency is being generated. So this is your zero time scale, and this is your sorry. So you can see here it is zero time scale, and here it is 255 microsecond. Okay, it's not that much stable. Okay, because we are having many lines of code inside that. Like we have a code. Yeah, we have a code like while true. Okay, while true, then while timer 0 interrupt flag equal to 1. So for doing this polling, it will require few more clocks. So that's why the clock was not stable. And one more thing to keep in mind, that the TMR0 always it may not be 0. Okay, the TMR0 can be set to some other values also, but if you write the TMR value, okay, then you have to be cautious that if the timer 0 register is written, the increment is inhibited for the following two instruction cycles. So in this case, if you write TMR0 is equal to 0, then instead of 256 microsecond delay, it will generate 258 microsecond delay. Okay, but it will not be 258 microsecond, it will be much more than that, because we have this line while TMR0 IF is not equal to 1. So to poll that, it will require few more clocks. Okay, so hope you have understood the timer 0 of PIC16F877A. Thank you.